Hello, and welcome to this Photonics Next Summit session, How Much is Your Photon Worth? Selecting Optimal Optical Filters, sponsored by IDEX Health and Science, Semrock. I'm Justine Murphy, an editor with Laser Focus World and Multimedia Director of Endeavor Business Media's Digital Infrastructure Group. Before we begin, just a bit of housekeeping. If you have any technical difficulties during this event, just use the questions window on the left side rail of your screen, and our technical experts will be happy to help. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. And we welcome your questions too for our speaker. You can send them at any time by using that same questions window, and we'll answer as many of those as possible during the Q&A session that will follow the main presentation. To refer a colleague to today's discussion, share it on social media, or access event resources, click the icons on the left side rail of your screen. And if you'd like to increase the size of the windows on your screen, just click the upper right corner. And please be aware that today's event is being recorded, and you'll be notified by email when that archive is available. And lastly, at the end of each session, a screen will pop up asking you to fill out a quick survey. Please do so, as this helps guide us on future content that we'll continue to provide. And now I'm happy to introduce our speaker, Dr. Michael DeLay, a Senior Application Scientist at IDEX Health and Science, Semrock. You can learn more about him in the Speaker Bio tab within the webinar player. And with that, Dr. DeLay, the floor is yours.
Thank you. So today I'm going to talk about selecting optimal optical filters, and I'm going to use a perspective which includes some relationship to this concept of the photon worth. So let me, I'll get into that in a moment, but first let me tell you a little bit about IDEX Health and Science. This is a group of companies whose has products over a range of relevant areas that are very relevant to the fluorescence assay and fluorescence microscopy, high throughput screening, things of that sort. So up at the upper right-hand corner where it says illumination, there is a set of icons that illustrate the kinds of devices that are made. So that would be objective lenses. There are filter laser devices as focusing devices. In the intermediate area where there's a green set of icons, there are objective lenses and tube lenses. The optical filters are shown there with a little four-colored wheel. There are microfluidics components that are shown in the orange tabs, and then off to the left there are a number of blue tabs or little boxes that illustrate the fluidics components. So, and these are then built into systems or subsystems, which are known for their efficiency, their innovation, and their customization. Now let me then introduce the Centers of Excellence Innovation. These are the two locations where filters are built and where the other devices are integrated. So Rochester, New York is the Center of Excellence. For us, that's where the filters are made, and there's also, excuse me, a significant amount of product building for the source of sensor systems and motion control and devices of that sort. And then in Carlsbad, we have the Center of Innovation, which contains R&D management, and also a lot of testing takes place there. So now let me talk about the topic here, which is the essentially fluorescence assays. So the photons arrive at detectors from various sources in a typical setup. And we understand that not all photons contribute constructively to the signal. This is part of the reality of biological experiments, that good photons, you might call them good, let's say, carry useful information about the assay. Bad photons carry signals that can negatively affect the assay, so noise, background, crosstalk. Autofluorescence, there's non-specific fluorophore binding. You can get photons that have made their way through filters which do not have as well controlled passband edge locations. There are filter pinholes and so on. So there's quite a range of obstructions to that can result in bad photons, let's say. Now, a robust assay, if you have one, if you're lucky enough to have that, may be less sensitive to the proportion of bad photons to good photons, but a more sensitive assay may need more good photons to succeed. So now we can focus a little bit, given this sort of simplistic view of good versus bad photons, at the optical filters and their role in affecting this balance. So we understand that specific filter properties will result in improving the good to bad photon ratio. However, it is also possible to do some cleanup or post-acquisition analysis to partially correct data. So if, for example, you have crosstalk, one can do some appropriate kinds of manipulations of the data to reduce effects of crosstalk, but manufacturing variability and other issues can set a limit on those. So obviously, if one can eliminate those using the filters, then that's certainly a better thing in general. So we would say then that optical filters can't improve every photon in your optical system to a good state, but it is, on the other hand, quite useful to have an extent to know how much filters, to what extent filters can make a difference, let's say. So, and that's what we will look at a little bit here. Coming back to IDEX Health and Science, this is, as I said, a group of companies has been designing and producing several families of optical filters. The design criteria of each of the families is more or less oriented around a well-defined envelope of performance. So that means that each family has a set of criteria, and those features can affect the balance of good photons and bad photons, which are passed by those filters. So that's one part of it. The other part is that each family tends to have a certain cost structure related in part to the cost of manufacture. And so, in other words, the customer is offered a choice of performance options at a choice of price points. Now, you might decide you just buy the best filter you can, something that's the most expensive with the best features, and it may have better rejection of bad photons than, say, a midline filter, which might be less expensive, but that may not always be necessary. It may not even always work unless you know the details, and it may also not be cost-effective. So if one thinks then about this idea of the worth of a photon, you can think of a photon having a worth which depends on its criticality or its usefulness. I don't mean the sense of photon worth where you have a number of fluorescent photons emitted by a molecule per unit time. That definition is not what I'm looking for. I'm using the concept of worth more as something that indicates the usefulness of the photon, or whether it's used in an assay with more demanding set of requirements. That is more of this idea of the photon worth. It's not necessarily a numerical value. It has perhaps multidimensional aspects to it. But in any case, part of the purpose of thinking about the worth of the photon is to think about doing a cost-benefit analysis that tries to relate this worth of a photon to the performance of the optical filters. So one could, for example, assess if a filter set has an acceptable price-performance ratio with respect to, say, noise or crosstalk. And that would then allow one to optimize filter selection. So the purpose here is to go through part of this cost-benefit analysis using a program called SearchLight, which is an open-use tool made by IDEX Health and Science. This is used for modeling photon flow in fluorescence-based optical systems. So in looking at different scenarios, I will draw some scenarios from, say, a more flow cytometry-oriented situation and others from epilumination microscopy. So let's take a look at SearchLight. that system, which is available on the web, searchlight.idex-hs.com. The SearchLight model is characterized by a box where you can see in the center, in the left side of this slide, there's a light source, with a yellow bulb. Following that, there's an excitation filter, a dichroic mirror. There's a deflection of the excitation beam down to an objective lens. Below that is a sample. And each of these pieces of equipment, let's say, has some spectral characteristic, which is why you see the letters T in connection with a wavelength. Once the light has been collected by the objective, it passes through the dichroic to the emission filter and then to the detector. So on the next panel to the right, which shows sort of a schematic of the wavelength on the horizontal axis and some spectrum on the vertical axis, one sees that there's two idealized optical filters denoted by a purple rectangle and a red rectangle. These are separating the excitation light from the emission light, of course. And then we have a fluorophore, which is shown in purple dashed line, which starts at the left and then peaks and then decreases. And then, of course, there's a comparable emission spectrum on the other side. There's a kind of brownish colored curve that shows the detector behavior as a function of wavelength, and there's also a light source. So all of these spectra and the different mathematical formulas and the behaviors are then modeled by SearchLight, as it indicates in the top right, to calculate the signal and the noise. And from that, it can also calculate the crosstalk and the bleed-through for multifluorescent situations. And one can build these sessions and share them with people, collaborators or others, using the web interface. There's also a large database of fluorophores, light sources, and so on. And one can also model individual filters if one needs to. So if one then looks at the SearchLight window in operation, there's a left panel which has a database of different components, so filters, fluorophores, light sources, detectors, and so on. Custom data can be added. The center panel shows the spectra, and you can customize this to make it easy to sort of see what's going on, so you don't have a million colored lines. And on the right-hand side is a list of all the selections that have been made, which are going to be used for the calculations at hand. And those you can organize into folders so that you can get a sense for what you're doing. So the lower part of the window then shows on the left side that one selects a combination of filters and filter sets and fluorophores that are used. And in the middle of the panel, one selects all these things from a drop-down list, and on the right-hand side, one sees then the outputs, which I'll get into in the next slide. There's also a lower panel with some optical parameters that are useful to when choosing the environment in which one's working. So that's where you model you have the parameters that control the modeling of the optical system. So on this slide, I'm showing, sort of paying attention to the special characteristics of the optical system. So there's obviously the light source power, which is up in the middle of the screen on the right. There's a numerical aperture of an objective lens. The reflected light excitation factor is something that is important. That is the fraction of the excitation light, which is essentially redirected from the excitation to the emission path. It comes from the sample and any kind of support structures around that, like a cover slip. And I've got 7% in there, which is perhaps a characteristic of an epi-illumination microscope, which is relevant because this is a situation in which excitation and emission processes share part of the same optical path. Other applications, such as flow cytometry, might have a much lower value, down to, say, 0.1 to 0.5%, because those systems capture light at 90 degrees with respect to the excitation beam, and there's not much commonality. On the top right, you see the fluorophore optical depth. That is the product of the concentration of fluorophore and the thickness of the preparation that contains that fluorophore. The next parameter down is the molecular absorption coefficient, which describes essentially how much light is absorbed by the fluorophore. And then the next point down, the quantum yield, then describes how much light is generated by that is the fluorescent light. The transmitted excitation light factors on the bottom left and right are numbers that tell you what fraction of light is transmitted through those parts of the systems. The autofluorescence light factor is something that is in the case of modeling autofluorescence. In this case, I have set that to 0. Now, the excitation light noise is a relevant parameter because it's very sensitive to the overlap and edge steepness of the excitation and emission filters. And it's also sensitive to the level and extent of the out-of-band blocking. So if you have inadequate blocking filters for the emission or excitation, you might expect rather large amounts of this noise, which then make what look like background. The signal-to-noise ratio that's calculated then is the fluorescence signal divided by the sum of the excitation light and the autofluorescence noise, which that latter term is, of course, 0. And these are typically in millivolts. So by way of applying this searchlight, I'll give you a couple of examples. One is relates to the sets that have been produced by IDEX Health and Science for common fluorophores. Those sets are called the BrightLine filter sets. They are denominated as in the box on the right. It says FITC, the name of the fluorophore, and then 2024. So 20 refers to the excitation bandwidth and 24 for the emission bandwidth. So this filter set, the BrightLine sets, have been introduced about 20 years ago. So they are an industry standard for quite a long time, and they've recently been replaced by what we call BrightLine 2.0. And what is interesting about the difference between BrightLine 2 and the original BrightLine is that the new ones have much deeper out-of-band blocking and greater critical edge steepness. Edges are steeper and the blocking is deeper. So those are the two parameters that happen to contribute significantly towards excitation light noise, as I said before. So, and if you look in the upper right-hand corner of the slide, you can see that the signal-to-noise ratio is 684, which looks quite good, and indeed it is. Below that is the replacement. You can see that the fluorescence signal is about the same value. But the signal-to-noise ratio is quite a bit different because the excitation light noise has been dramatically reduced. So clearly the new set has a much greater signal-to-noise ratio. And so the question is then, why is that important? Well, suppose that you have low signal, let's say by a factor of 10. Now you have a signal-to-noise ratio of 68. Well, that is now getting to the point where you may start having issues with data interpretation. Low signal levels, after all, can occur due to low concentrations of fluorophore. Maybe the signal changes are small due to the experiments. You might have high noise levels, that is more backscatter, because you have a turbid preparation or because you're using intact tissue, which is fantastic at scattering. And so we see that BrightLine 2.0 is much more immune to this kind of signal diminution compared to the original BrightLines. The other interesting point is that these BrightLine sets are essentially cost-neutral improvements on the original sets. So, and I think in a way one can say then that the BrightLine 2 sets increase the photon worth by increasing the proportion of good photons that they deliver to the preparation and to the detector. So take two more examples, again with the same fluorophore. And now we're considering, let's say, normal to high levels of excitation. And we have then talking about the BrightLine 2.0 filter versions. That's why it says BL 2.0 in the filter set column. In this case, we have uniformly very good excitation light noise for all of these filters. Now, we do have one other filter set we've introduced, which is the FITC Basic. This has been around also for quite a while. These filters are somewhat less cost, as you can see from the second column, cost relative to the 2024 FITC filter. Now, the two rightmost columns then show the signal-to-noise ratio, again, for high levels of excitation, high levels of light, let's say. Both of them are really quite similar. That is, whether you use laser or whether you use xenon, the rhodamine crosstalk is pretty much the same. The interesting point about this is that the FITC basic sets seem to do rather better than the other two, the 3540 and the 5050, which of course have larger, they have wider pass spans for both excitation and emission. So that is something that one might not anticipate on the basis of the name and so on. So I would say then that the FITC basic represents good value for intermediate performance, in this case. I wouldn't say that all of these basic filter sets are that way, but certainly one can check that. It's simple enough to check. Now, let's try then one other, which is similar sort of thing, but now let's use very, very low light levels. That can be the case in a situation where you have relatively little, say, small individual cells, a few of them that are being looked at, or some kind of small bubbles containing fluorescent material that are traveling through, say, a small pipe. And so here we're not looking at crosstalk, we're looking only at excitation light noise in two situations. One, laser, and the second one, a broadband lamp, such as xenon. So the cost information in the first two columns is the same, but you can see that the laser results in very, very, very good excitation light noise compared to the xenon, because the xenon lamp, since it has a broad spectrum, that spectrum contributes to the noise level at the detector, and therefore is not that effective. So one would conclude, of course, that the laser is a better way to look at this signal. This is, of course, not a surprise. What is maybe perhaps a little bit of surprise is that the FITC basic filter does not perform that well. So there is a situation where, again, you might not anticipate this, but it may not be a rule, but it can be checked. So this is the idea of cost-benefit analysis, which relates to this criticality of a photon. So let me summarize this by saying there is, let's say, a pain point here. Optical filters may not perform as intended, or they have too high a cost. And from that arises a challenge, which is to define a robust strategy to characterize and choose them, where cost control is explicit part of it. And the solution in this kind of situation is to think about a cost-benefit analysis using SearchLight and perhaps other tools. And then from this, you could expect a rational choice of filters that are costed appropriately and are chosen for adequate performance. So that is the end of my talk. And I thank you for listening to this.
Great. Thank you so much. We are going to move into the Q&A now. As I mentioned before, if you'd like to submit a question for Dr. DeLay, just use that questions window. And we do have a few in here already that we have time for, so let's jump in. Suppose I want to buy a custom optical filter. What are major cost drivers and which are minor?
Yes. So I think in general, it's the case that these steep edges I referred to are a cost driver. We find in making filters with these steep edges that approximately half or a little bit less than a half of the cost of the filter can be related to the steep edges. So steep edges are certainly a cost driver. The other part of that, of course, is the blocking. Blocking is, of course, also does cost. The other point to sort of look at here is that if you want sort of a very demanding flatness and wavefront properties, that can also drive cost.
Okay. Is it more cost effective to use off-the-shelf filters or invest in custom designed ones for specialized applications?
Yeah, that's one of those questions. I think for prototyping, one could envision that use of catalog filters is quite reasonable. So that is certainly a more cost-effective way to go. The problem is that at some stage, if you need something a little different, then you are going to be, in any case, in a situation where something custom would be needed. So there are many situations in which catalog filters will work perfectly well. In that case, one can transition those into a production situation and continue. So it depends to a great extent on the requirements.
Okay. Well, unfortunately, we are nearly out of time. Any questions we didn't get to today will be addressed directly later via email. And once again, there will be a quick survey that pops up when we're done here. Please do fill that out. It helps guide us on future content that we'll continue to provide. And don't miss our next session, which you can join by exiting out of this one, going back into the agenda and clicking on the View Sessions button. So on behalf of Laser Focus World and Endeavor Business Media, I'd like to again thank Dr. Michael DeLay for a great presentation, IDEX Health and Science Semrock for sponsoring this session, and of course, all of you too for joining.